at how to take that Prolog backtracking and unification mechanism that is Turing complete, and then actually use it to solve problems that we solved back in the first programming course using Python. So this idea of how to take the computations that you express with the while loops and if-elses and for each loops and rewrite it in Prolog, but then hopefully in Prolog also make it better so that it's reversible and can make general queries. So the basic technique that is needed is the tail recursion. And the tail recursion, it's the same idea applies in all programming languages, even imperative languages. The idea of a tail recursion is that you solve the problem recursively. You spot the self-similarity with the Prolog list and the tree structures. The self-similarity is usually the tree that to solve a problem for a list, solve it for the head and then solve it for the tail, or to solve a problem for a tree, so solve it for a subtrees and then from that the solution to the complete problem. But the tail recursion, so it's better recursion, is that the recursive call is at the end of the body of the function. End in the sense, not necessarily syntactically the last thing, but the recursive call is the last thing that is done during the function execution. And the same idea for this backtracking predicate evaluation. So let's say here in the tail rec demo that I've been using as an example, I'm gonna be using as an example in the class. So implementing bunch of list predicates, first the non-tail recursive way and then the better tail recursive way. So these examples, along with the examples that we go through after this, should show you how to change your thinking from while loops and for loops and if-elses into these Prolog rules. So max list. So first the recursive version. So max list rec. So 17, 99, 42, minus 8, 44. So what is the maximum of that list? So turns out to be 99, and then we also have a false choice point in the end, so we can think how to get rid of that with the cuts without breaking the generality. So the recursive rules, so first here in this non-tail recursive, so the rules often for this list is that the base case is for an empty list. Well, empty list doesn't have a maximum, it has a sum to 0, but it doesn't have a maximum. And the base case notice is a one element list. So on line 5, so max list rec says that for any one element list, that one element itself is the maximum. Fair enough. And then the thing that's leaving the false choice point, we can see how we can fix that. So max list rec with the list that has a head and a tail. Now this will still match a one element list because tail can be empty. But you will first calculate the maximum of the tail. So let's call that m. And then with the arithmetic, so max is a arithmetic function. So functions are just special case of predicate. So max is in reality a three arity predicate where the result is here the invisible, but the predicate that has been defined that it can be used as a part of arithmetic evaluation. So then the result then becomes the result of the evaluation instead of being bound to the third parameter, and then we just do the unify afterwards. So now the recursive call, we see that it's not a tail call. So it's there inside the body and then stuff happens afterwards. So now the deep recursion, the stack has to necessarily grow because the stack frames cannot be reused. So then this is gonna run out of stack when run on a really long list. Then as we'll see in the later examples, so tail recursion can also speed up the execution, but doesn't do so here. So first calculate recursively the maximum of the tail of the list, and then whichever of the two, the current head and the tail maximum is larger, then unify the result with the x. So usually this parameters that we think of as a result, still thinking in a forward operational direction instead of symmetric logical thinking. But so we realize that we cannot evaluate the max HM before M has been bound. So we cannot turn this into tail recursion by swapping the order, because now if we try to make the same call, it's just gonna give us that this M hasn't been instantiated, so cannot be. So it is not quite this easy to convert the recursion into tail recursion. We gotta do something else, but something else that we do is totally mechanistic. So all these examples do the conversion the same way. So once you see how this conversion works, so then you can use it in Prolog. And we use a tail recursion to simulate the while loop. So now if you think about how you would solve this problem with the while loop, or a special case of a while loop, the for loop, so then this thinking tells us how to solve these problems in Prolog. So let's look at the tail recursion version, and then the term accumulator. So the accumulator is the technique that is used to take a non-tail recursive function or a Prolog rule. So this same technique works for imperative language. It's a good technique to know. And then what is called an accumulator. So then extra arguments. So all these steps are the same. We're gonna read through all these examples in these videos, and I'm gonna emphasize that all the steps are the same. So the conversion is totally mechanistic. So this top level call. So then the max list. For a list that contains at least one element, then it's gonna be X, but X is probably gonna be unbound at that point. So we make a version. Notice that we can have like a method overloading in other languages. We can write the predicates with the same name with the different arity. So we have this one takes 2 parameters, and this one takes 3. So Prolog is not gonna have a problem telling which predicate you're using, even when they have the same name. So of course you could give it some other name also, but we don't need to do that here. So if you think about how a while loop works, so if we did this in a Python or Java, so we have this, this would be like the parameter that is received, and then this is the result that we're returning. And then in the while loop, you would have some other state variables. So here you would have the current maximum. You keep track of that in a separate local variable. So all these local variables that you have in the while loop, so in addition to the function arguments and the result, so you simply turn them into additional parameters in this higher arity version. So if your while loop solution suppose had 2 local variables, so then you would have 2 extra parameters here in the end. I put consistently all these extra local variable parameters in the end, so keeping all these original parameters in the same order, so it's easier to follow what happens. But of course, so then the order of these parameters, so it is whatever you choose it to be. So pick an order and then be consistent with it. And then the base case, so it's always gonna be pretty much the same. So the base case for this empty list, so once this first parameter is an empty list, so then this result, which here is the X, so remember, because variables, once you bind them, you cannot reassign them. So all this X, so if it's unbound, throughout the entire tail recursion, X is kept in an unbound form. And then so in this base case, so it looks kind of strange, but all this is saying is that the result is gonna be unified with the value of this local variable that we are simulating in this other argument. We could also write it this way to say that I used the term max so far. Maybe it's actually better this way to say that at the base case, so we take this accumulator variable and then say with the view of a result of a Prolog unification is that the result is gonna be now bound to the current value of max so far. So it's not wrong to say this way. It's just redundant. So in generally, So whenever you use explicitly the unification in your Prolog code, usually that use is redundant, not always, but like here. So this would be a common beginner mistake, I know, that so to say that the two variables have to be the same. You can say it this way, or you can just say right there in the definition that they have to be the same. So at the base case, so take the current value of this extra accumulator parameter and force the unification of the result to the current value. So when we are looping through the, not looping, but recursing through the list, so max so far, this argument always, this parameter always has the current maximum, and then at the end when we have processed that, there's nothing left, so the result is gonna be equal to the current maximum. And then the use of this accumulator parameter, the fact that we extracted the simulated local variables of the while loop that we're thinking is behind, we're thinking in the imperative terms, is that now we can just write rules. So rules for the body of the loop say that if the variables at the beginning of the body of the loop are this way, then at the end of the body of the loop they're that way. So we just make this a tail recursive call to itself. So it's executed in the same stack frame, and it's efficient and cannot run out. So if in the loop, so notice that it's now very important again that these two rules are mutually exclusive. So this one matches the empty list, the base case, and this one matches any non-empty list. So then there is no choice in here. This is completely deterministic. So of course a tail recursion can be made to have a choice. So we take all the, but so when a predicate is inherently deterministic like this one, so if there's not supposed to be a choice in there, then there shouldn't be. Okay, so if this is the state that the current list consists of a head and a tail, and the unbound max x is still kept there as in the unbound form, and we remember the maximum so far, so from the previous levels of the recursion, so this accumulator always travels down, so then we calculate the maximum of the current head and the maximum so far, and then in the next call, so then now that we process the head element, so we're supposed to process the tail. Important always to make sure that in every recursive call the thing gets smaller. So if your subproblems don't get smaller, you're stuck in an infinite recursion. So find the maximum of the tail, remembering that M2 is now the, I guess I could call this M because I must use the. So M is now the new maximum so far. Notice it's so very tempting, like inside the rules, to say something like a new x. The x is 42, and then to say x equals x plus 1. But of course, this cannot possibly work because so once x is 42, so and even with the is, it still wouldn't work because 42 is not the same. So once a variable has been assigned, you cannot reassign it. So then you have to make up a new variable. So here, so M, so we always have to make a new variable name when we mean a new value that is in the call. So this is now, let's wrap up this video, and in the next video, look at a couple more. That the general idea that when you have a recursion, so do this first, so always get it to work first, so simple enough, don't need to think. But we realize, no, this is not tail recursion. We really want it to be tail recursion, so conversion is mechanistic. Step 1, so then take this top level call and have it to call the version of the predicate with the same arity, with extra parameters corresponding to the local variables that you would have if you were writing this as a while loop in Python or similar. So this one, so the head element in the beginning, so it becomes the largest so far, and then we just process through the tail. The base case, so unify the result variable that is gonna be kept in the unbound form down the recursion, unify it, so typically unify it with the state variable. It could be that you have like a one line of code in here to say that the result equals the sum of two state variables or something, but usually it is like this kind of to say, force the unification of the result with the state, and then body of the while loop. So if there was a if-else, you would have two different situations. Then you have two different versions of the rule matching different situations. But here, so there is just to say that if in the beginning of the body of the while loop, you have a list that consists of a head and a tail and the unbound result and your current maximum from the previous levels. So then calculate the new maximum and make a recursive call.